Good day everyone. Today I will be discussing another topic in machine elements. This topic is about acceleration analysis. Just a quick recall, we discussed in topic number 5 velocity analysis. So there are 4 methods that were presented in that topic. The topic of velocity polygon method is very important in this topic. By the end of this topic, you should be able to describe the importance of acceleration analysis in the design of mechanism. Use the semi-graphical methods of acceleration analysis to solve linear and angular acceleration and linkages. And compare velocity analysis and acceleration analysis. Maybe right now you are asking what's the importance of acceleration analysis. With the advent of high-speed machines, the accelerations of the moving parts are becoming more important. The inertia forces produced by the accelerations of the links in a machine may be of a high magnitude, and in some cases, at a certain position, may be higher than the forces produced by the working medium. The obtaining of the accelerations of points in the links of machine is prerequisite to the making of an inertia force analysis of the machine. Once we have these forces, we can use the formula force is equals to mass is equals to acceleration. The acceleration in that formula will be the one that we will get in our analysis. So these dynamic forces is important because they contribute to the stresses that these links and other components may experience in actual practice. An important concept here that we must understand is the concept of velocity components. Velocity can change in magnitude. It can also change in its direction sense, and it can change in both magnitude and direction sense. A particle whose velocity changes both in magnitude and direction at any instant has two components, and these are the centripetal, which is also called radial or normal component. This is the rate of change of velocity in the direction sense, or which is perpendicular to the velocity of the particle at a given instant. On the other hand, we have the tangential component, which is the rate of change of velocity in magnitude. It is parallel to the velocity of the particle at the given instant. So what is acceleration? If you can recall, acceleration is simply the rate of change of velocity with respect to time. It is a vector quantity and can either be linear acceleration or angular acceleration. Linear acceleration is defined as the rate of change of the linear velocity, while angular acceleration is the rate of change of the angular velocity. To illustrate the difference between the radial, the normal, as well as the tangential component of the acceleration, let us look at this figure here. Consider 2 points here, A and point B, on a rigid link. So this is a rigid link, say one of the linkage in our 4-bar mechanism, for example. This is represented by this figure here. So let the point B moves with respect to A. So point B is a point that rotates at the point of rotation, which is point A. It has an angular velocity of omega, represented by omega in rad per second, and it has an angular acceleration represented by alpha in the figure. So we have here omega, and then we have here alpha. So the direction is the same. So meaning for point B, it would rotate counterclockwise. So for this link AB, the velocity of point B with respect to A, so its velocity with respect to A is perpendicular to the link AB. as you can see here. So the velocity of B relative to A is this line here, which is perpendicular to the link AB. Since the point B moves with respect to A with an angular velocity of omega, also its centripetal or radial component of acceleration with respect to A is this line here that you can see. So this radial component of acceleration acts parallel to the link AB. So as you can see, the radial component of the acceleration of B is parallel to the link AB, and its direction is towards the center of rotation. So this is the arrowhead. So this means that the radial component of this point B is towards point A. On the other hand, its tangential component acts perpendicular to the link AB. So this is represented by this one. So we have alpha to the power of superscript T and subscript BA. So this is the tangential component. So you can see here that the components are perpendicular to each other. The direction of the radial component is towards the center of rotation. On the other hand, the direction of the tangential component is the same as that of the alpha, or the angular acceleration. So for computing the value of the radial component of the acceleration, so this is denoted by this alpha to the a to the power of r and with a subscript BA. So this is the radial or normal component of the acceleration. We can compute that by using the value of the omega squared multiplied by the radius, which is the AB. So that is how we get the value of the alpha, the radial component or the normal component of the acceleration. And since we know that the angular velocity is equivalent to velocity of B relative to A divided by the radius, which is AB, so we can also write it in this form, such that our radial or normal component of the acceleration of point B relative to A can be computed if we have the velocity of B relative to A to the power of 2 divided by the radius of gyration, which is AB. So therefore, to get the radial component, all we have to get first is the velocity of a point divided by its distance from the axis of rotation. So just like here, the velocity of B relative to the axis of rotation A divided by the distance of B to A. So that's how you get the radial component of the acceleration. So again, its direction is towards the point of rotation. On the other hand, for the tangential acceleration, or the component which is tangent to the normal acceleration, can be computed using the formula, the angular acceleration alpha of that particular link multiplied by the radius or the length of the link. So the tangential component is its direction is the same as direction of the alpha. So wherever the alpha is also the direction of the tangential component of the acceleration, and it can be computed using this formula here. So that is how we defined the radial as well as the tangential component of the acceleration. Acceleration diagram. Acceleration diagram will help us in our analysis of the acceleration because it will simplify our analysis and it will aid us in computing the unknown acceleration. Say for example, you have here again the same link with 2 points A and B, where point A is the axis of rotation and B is a point that rotates with respect to the axis of rotation A. From the given length, which is AB, and angular velocity omega, we solve for the velocity of B relative to A. So we already know how to compute that. Next is we solve for the radial and the tangential acceleration using the two equations that we have earlier. So we have the radial component and then we have the tangential component of the acceleration. Once we have that, from any point Q, we draw the vector length equivalent to our radial component of the acceleration of B relative to A parallel to the link AB to represent the radial component of acceleration B, because we know that it acts parallel to the link AB. Say for example, we have your point Q, so we draw the equivalent radial component using a line that is parallel to the link AB. So once we have that, from the terminal of that component, we draw the vector length, which is tangential, which is perpendicular to that radial component to represent the tangential component of the acceleration. So from its terminal or its head, so we draw the tangential component of the velocity of B, of the acceleration of B relative to A. So you can see here the radial component and the tangential component. To draw a line, we draw a line from Q to the terminal of the tangential component of the acceleration of B relative to A. This represents now the total acceleration of B relative to A. So finally, we were able to get the absolute or the total acceleration of B relative to A. So that is the value and that is also its direction. So that is how we can use the acceleration diagram in solving the different accelerations. The direction of the angular acceleration alpha is not always the same as the direction of the angular velocity. If the angular velocity is counterclockwise and the alpha or the angular acceleration is clockwise, so meaning they are in the opposite direction, that means that the link is turning counterclockwise because it will follow the direction of the angular velocity. But since alpha is opposite, it means that it is decelerating. On the other hand, if they are rotating in the same direction, it means that the link is accelerating. So that's how you can interpret the direction of the omega and the direction of the alpha and their relationship with each other. The direction of the tangential acceleration, which is denoted by alpha t, is always the same as the direction of the angular acceleration. So that is how you can also find the direction of the tangential component, because it will always be the same as the direction of the angular acceleration. So we will illustrate that later on. So let us define another term, which is total acceleration. The total acceleration is the resultant linear acceleration of a point B relative to A, which is obtained by solving vectorially the following equation. So we have here, so the total acceleration of B relative to A is just the vector sum of the radial and the tangential component, as you can see here in the diagram. The angle is the resultant acceleration vector direction with respect to the link AB and is expressed by the equation that you can see in the slide. So we can express that in terms of the alpha and the angular, the omega or the angular velocity. So that is the total acceleration. So that is how you get the total acceleration if we know the radial and the tangential component of a point with respect to another point. So let us remember that the absolute linear acceleration of one point on a floating link is equal to the vector sum of the absolute linear acceleration of the second point on the link, the normal acceleration of the first point relative to the second point, and the tangential acceleration of the first point relative the second point relative to the first point. So in equation form, we can write it this way. So say for example, you are looking for the acceleration of point B, and you know the acceleration of point A. So if you are to get the acceleration of B, you can use this relationship that the acceleration of B is just the sum of the normal component of the acceleration of B, the tangential component of the acceleration of A, the acceleration of B relative to A normal, and the acceleration of B relative to A tangential. Take note that these are vectors, so this means that you will add both the magnitude and the direction. A method that will help us in analyzing the acceleration of the different points in the linkages is what we call the relative acceleration method. Say for example, you have two unknowns, the acceleration of B and the angular acceleration of AB. So we wanted to know the acceleration of point B, and also we wanted to know the angular acceleration of the link AB. So take note that the angular acceleration is the same now for all of the points in this link. So we wanted to get this unknown. So what is known to us is the velocity of A as well as its acceleration. We also know the direction of the velocity of B, that is denoted by this direction N. So this is the velocity direction. M, on the other hand, is the direction of its acceleration. So what we wanted to know is the value of the acceleration. So we can use this relationship that we defined a while ago. So to get the acceleration of B, we need those four components. Take note that we can also write that equation in this way. So we have the acceleration of A, which is the sum of the normal and the tangential component of the acceleration of A here. So this two part of these four terms can be represented simply by the acceleration of A because they are equal. So the acceleration of A is just the normal component of A plus the tangential component of A. So this is the value plus, so the normal component of the velocity of B relative to A can be written in this form based on our previous formula. So that is the velocity of B relative to A squared divided by the length of the link AB. Then finally, we add the tangential component of the velocity of B relative to A, which is denoted by this formula, which is alpha, or angular acceleration of AB, multiplied by the length AB. So we draw the velocity polygon first because it will help us to get the relative velocity. So take note that in the previous formula, we need to get the relative velocity of B with respect to A. So that's why we can use the relative velocity polygon method in order to draw the velocity polygon. So in doing that, we select a pole Q, and then from that pole Q, we draw the direction of the velocity of A. So this is the velocity of A. So we just draw that from Q because the velocity of A is known and its direction and magnitude is also known. So we can draw that in the velocity polygon. So next is we draw the direction of the velocity of B. So we know that the velocity of B is represented by N. So that's why we draw it also at Q. So that is the direction of the velocity of B. And then we draw a perpendicular line from Q perpendicular to AB. And that will touch the terminal of A, because the intersection of the direction and this line is the velocity of B. So you can see here, the velocity of B is now known to us. So this is the velocity polygon. So from this velocity polygon, we can measure the value of the AB. So this AB represents the velocity of B relative to A. So now we can compute the acceleration of B relative to A normal because we already know the velocity of B relative to A. So we just measure this and multiply with the velocity scale squared divided by the length of AB. So the AB here in the actual drawing. So that is the normal component of the velocity acceleration of B relative to A. Now that we have the normal component of the acceleration of B relative to A, we can draw the acceleration polygon. So we select again another pole Q. So we draw first the acceleration of A. So we can see that the direction of the acceleration of E is downward, so that's why it's also downward here in our acceleration polygon. So the acceleration polygon is somewhat the same as that of our velocity polygon. So it is a mirror also of the actual linkage. So that's why we can see here that the direction should also be the same. And from that, we will draw the value that we computed, which is the acceleration of B relative to A normal. So you can use again a acceleration scale this time to draw it from the head of A. So because this is the normal component, and we know that the normal component or the radial component is moving from the point to its point of rotation. So since B is rotating with respect to A, so that's why the direction of ABA normal is going to A. So that's why you can see it here. So we add it from the head of the acceleration of A based on our formula. So now we have the acceleration of B relative to A normal. So its direction again is towards point A, and its value is computed using the velocity of B relative to A squared divided by the length of AB. And then for the tangential component, we know that it is tangent to the link. So you can see here the link is AB. So the tangential component of the link AB must be tangent to that. So that's why we draw here a line that is parallel to that tangent lines from the head of the ABA normal. So that is the direction of the tangential component of the velocity, the acceleration of B relative to A. So now that we know the acceleration of B relative to A tangential, its direction, and since we know that the absolute acceleration of B has its direction denoted by M, then we can draw that from pole Q because that is the absolute value of the acceleration of B. So we draw that from the pole Q, and then its intersection with the tangential component now represents the acceleration of B. So therefore, we're able to get the acceleration of B. So you can see that those arrow that originates from Q are the absolute acceleration. So this QB, for example, is the absolute acceleration of B, and QA is the absolute acceleration of A. So that means that if you want to separate them in components, then we can separate them in both normal and tangential components. You can also see here that we can verify our formula that the acceleration of B is the sum of the vectors AA, ABA normal, and ABA tangential, as you can see. So we just added using head to tail, and then we draw from the original point to the head of the final point. So that's why this represents now the acceleration polygon. So for the question, the final answer would be the acceleration of B would be the measurement of QB multiplied by the acceleration scale. On the other hand, the angular acceleration of the link AB, so this link AB here, its angular acceleration is the acceleration of B relative to A tangential divided by the length of that particular link, which is AB. So we were able to get the different unknown using the formula that we have. So that is how we can use the relative acceleration method in finding the unknown acceleration, be it linear or angular. So you take note that the direction of the ABA normal is towards A because A is the point of rotation. So do not forget that one. So let us have an example. So we have here a crank and a rocker mechanism that has the dimensions as you can see here. So the dimensions are shown in the drawing. The crank 2, so crank 2 has an angular velocity of 200 revolution per minute. So this is your crank 2, Q2. So this crank 2 here has an angular velocity of 200 revolution per minute. So denoted by this omega. So it is counterclockwise. So that's why the direction is counterclockwise. And negative angular acceleration of 280 radian per second squared. So if we say negative angular acceleration, that means that it's opposite the direction of the angular velocity. That's why alpha here is opposite because it's decelerating. It's a negative angular acceleration. So the value is 280 rad per second squared. For the position shown here, we wanted to determine the instantaneous linear accelerations of A, B, C, and D, and the instantaneous angular velocities and angular accelerations of link 3 and 4 using semi-graphical approach. So again, we will get all of the acceleration, the linear, and then we will get the instantaneous angular velocities and also acceleration. We will use the semi-graphical approach. So the step 1 would be to draw the mechanism to scale by using the appropriate space scale. So if you're given, for example, here with 10.5 inch, so that is almost one ruler. So it cannot fit in your paper. So in order to make sure that these dimensions will fit in your paper, you will use the space scale. Say for example, 1 inch represents 12 inch in the given, then this 12 inch will be 1 inch in your paper. So that's how you can use the space scale. So that would help us to have a convenient velocity and acceleration scale. So for this problem, I chose the space scale of 1/4. So meaning all of the actual sizes here will be 1/4 in the drawing in the paper. So meaning you divide the dimensions by 4. So meaning 12 will become 3 inch in the drawing, and so on and so forth. The velocity scale is 5 feet per second. So meaning 1 inch in your drawing is 5 feet per second in computation. And then the acceleration scale is 100 feet per second squared. So how would you choose this? It's actually dependent on you. The result would still be the same as long as your process is correct. So the key is really to choose the scale that will make your drawing more convenient. Step 2 is to compute the value that we can already get. So from the given, we are already given with the revolution per minute of this link here, which is represented by Q2A. So therefore, we can get the velocity of A because we know its angular velocity, right? So if we know the angular velocity of the point, we know its distance from the axis of rotation, then we can also get its absolute linear velocity. So the velocity of A, so the velocity of point A would be 2 pi q, q2A multiplied by n, then you divide it by 12 and 60 because this represents the conversion from inch to feet and from minute to second. So that's why if you plug in the value from the given, which is 200 RPM and 9 inch, because Q2A is 9 inch, as you can see here, it's 9 inch. Therefore, our velocity of A is 15.7 feet per second. So since our velocity scale is 5, so in your drawing, you divide this one by 5. In the paper, you can draw the velocity of A as 3.14 inch. So that is 15.7 divided by 5. So again, 5 is the kV or the velocity scale. So 3.14 inch will represent the velocity of A in our paper later on. On the other hand, since we already know the velocity of A, we can now get also the normal component of the acceleration of A. Using the formula, the velocity of A squared divided by the radius, which is q to A. So substituting the value. So take note that we will substitute the actual value, not the scale value. So we can get here 328.8 feet per second squared. And since our acceleration scale is 100, so we divide 328.8 by 100, and then we obtain 3.288 inch. So that means that in our paper, the acceleration of A normal is 3.288 inch. So that is the acceleration of A normal. And for the acceleration of A tangential, we can use the value of angular acceleration alpha because it's also given. So alpha, which is the angular acceleration of this link, where A is also connected, so that's why we can use that here. We multiply it with the radius of q to A. So it's given as 280, and then we convert it to feet, so that's why our result is 210 feet per second squared. And using our acceleration scale, we can get 2.1 inch as our tangential component. So now we already have the velocity of A absolute, the acceleration of A normal, and the acceleration of A tangential. So we will use these values later on. Step 3 is to draw the velocity polygon. So this is why mastery of the fourth method of velocity analysis is very important and critical in this topic, because we will have to draw the velocity polygon for us to get the value of the relative velocities. So the velocity polygon can be drawn by first selecting a pole Q. So we select a pole Q anywhere, and then from that pole Q we draw the velocity of A. So it can be drawn by drawing a line that is perpendicular to Q to A in the actual drawing from the point Q. So that's why we have it here. So you can see that this line is perpendicular to Q to A, because that is also the direction of the velocity of A. So since we already calculated a while ago the velocity of A, then we can plug it in here. And since how can we know that the direction is towards upward and not downward? So the direction of the velocity, take note, is the same as the direction of the omega, or the revolution per minute, or here the RPM. So they have the same direction, so it follows the direction of n or omega. So that's why it's in that direction sense, as you can see in that arrow there. So now that we have that velocity of A drawn in the velocity polygon, we can also think now of another point that we will get. So you can see here there are other points like B, point C, and point D. So the technique in choosing the next point is to select a point where we know the direction already. So take note that if we know the direction of another point, then we can use the methods that we already know to get the absolute velocity also. So among the points B, C, and D, only one point has a known direction of velocity, and that is point B. How do we know that? We know its direction because it is connected to Q4, which is an axis of rotation. So if we know that if a point is connected to an axis of rotation, the direction of its velocity is perpendicular to that link. So that's why the direction of B is perpendicular to Q4B. So that's why we draw first a line connecting AB, because wanted to get the direction of the absolute value of the velocity of b. So we draw a line connecting AB, and since B is connected to A, that means that B has a velocity relative to A. So we have a relative velocity of B to A. So we can get the velocity of B relative to A. So to draw that, since it is a relative velocity, so for relative velocity, we will draw it from the head of the known velocity. So the known velocity is A. So we draw a line from the terminal of that velocity here in our velocity polygon, and we make sure that that line is perpendicular to the link AB. So you can see here it should be perpendicular. So this is the direction sense of the relative velocity of B to A, or the velocity of B relative to A. So the good thing now is that we know the direction of B. So that's the reason why we select a point whose direction of velocity is known. So we draw again a line connecting Q4B, and then perpendicular to that line is the direction of the velocity of B. So therefore the velocity of B is the intersection of the point of the two lines that we have drawn earlier. So we can get now the velocity of B, and that is the QB. So now that we already have the velocity polygon in terms of the velocity of A and the velocity of B, we measure it using a ruler. So here I measured it. The length of AB is 1.44 inch and the length of QB is 2.32 inch. So we will use that later on in computing the value that we wanted to get. And those are the normal components of acceleration. So that is the acceleration of B relative to A normal. So it means that the acceleration, the relative acceleration of B to A normal, which is the direction is towards A. So that direction of that normal is towards A, because A here now represents the center of rotation of B, because it's relative to A. So we compute that by using the formula velocity of B relative to A squared divided by AB. So the relative velocity of B to A is the value AB in our velocity polygon. So that's the importance of the velocity polygon. So we measure that, and since it is inch, so we need to convert that first to velocity by multiplying it with kV, so that it will be feet per second. That's before we square it and we divide it by the length of 15, which is the link AB. So since it is inch, we divide it by 12, and then now we can get the acceleration of B relative to A normal, which is 41.5 feet per second squared. So using again our acceleration scale, we divide it by 100 and we get 0.415 inch. So therefore, later on when we draw the acceleration of B relative to A normal in the acceleration polygon, it will be 0.415 inch. For the acceleration of B relative to A, acceleration of B normal, so we know that the acceleration of B normal is its acceleration relative to the axis of rotation. So that is Q4. So take note that B rotates with respect to Q4. So it has an absolute velocity relative to 4. It has a relative velocity relative to A. So the value of acceleration of B relative to A, the acceleration of B normal, can be computed by the velocity of B squared divided by the distance Q4B. Or simply that is this its velocity here perpendicular to this link Q4B divided by the length of the link Q4B. So using the velocity polygon, we get the value of QB, which is 2.32 inch, and we multiply it by the velocity scale, and then we square it, and then we divide it by the distance Q4B, which is 12. And then we can get the acceleration of B normal, which is 134.5 feet per second squared, or in our acceleration scale, that is 1.345 inch. So take note, we will use these normal components of the acceleration of b relative to a normal and the acceleration of b normal when getting the acceleration polygon. So now that we have those values, the next step would be to draw the acceleration polygon. So how to draw the acceleration polygon? So first we'll locate Q at a convenient place. So say here. And then we draw the value that we already computed a while ago, which is the acceleration of A normal. So take note that the acceleration of A normal has a direction towards Q2 because it is the normal component of A, its acceleration is towards the center of rotation. So we draw a line parallel to that from Q, whose length is 3.288 inch, which we computed using the space scale. So this represents the direction of the acceleration of A normal. So that is the acceleration of A normal, equivalent to 3.288 inch. So you can see that the direction is the same as the direction of this line here because it will rotate. Its direction is towards Q2. So the AA normal has a direction towards the center of rotation of A. And for the tangential component of A, we already computed it also, that is 2.1 inch, that is tangent to this line from its terminal. It represents the tangential component of the acceleration, absolute acceleration of A. So we draw that. So it's tangent. So as you can see, the direction of the tangent is in that sense because if you can remember, the direction also of our acceleration is towards this, towards clockwise. So that's why, again, tangential component of acceleration has the same sense as that of the alpha. So that's why it's going in that direction, and it is perpendicular to this link Q to A. So now we have the component of the acceleration of A, which is the normal and the tangential. So in our formula, we can get the acceleration of A by using the head to tail method. So we locate A by using head to tail. So from the tail or the pole Q to the head of the last point, which is the tangential component. So that now represents the acceleration of A. So that is the direction of A. As you can see, it's very different from the direction of the velocity because the velocity of A is towards this direction, as you can see in the velocity polygon. Whereas in the acceleration polygon, the acceleration of A is very different direction. So again, this is the acceleration of A, or the absolute acceleration of A. And these 2 points here are the components, the normal and the tangential components. So we're able to get now the first unknown, which is the acceleration of A. So next, we'll locate the acceleration of B. So take note that we can get the acceleration of B because we know the relative velocity of B to A as well as its normal components. So first, we will draw the value that we computed a while ago, which is the normal component of the velocity of B relative to A normal. So as you can see, this normal component has the same direction as this AB here because now we will imagine that A is the center of rotation of B because it's relative. So B will rotate with respect to A, therefore the direction of its normal component is towards A. So that's why we will draw that line parallel to AB. So that is the ABA normal. So the acceleration of B relative to A normal. So the length again is 0.415 inch. So we draw it here from the head of the absolute acceleration of A. So that is this small line here. So that is the normal component of the velocity of B relative to A. So the direction again is towards there because B has a direction, has a acceleration relative to A. So A is the axis of rotation. So the direction of its acceleration would be towards A. So that's why the direction here is going in that direction also, not upward but downward. So we also draw the tangent because tangent will always be tangent to the normal. So from the normal we draw the tangent. So the direction of the tangent is also tangent to what? To the drawing. So we have here, so these two lines now are parallel. So this one AB, this line here is tangent to AB. Same also here. This tangential component of B relative to A is also tangent to the ABA normal. So meaning it's 90 degrees here. So this is the acceleration of B relative to A tangential, or the tangential component of the acceleration of B relative to A. So we do not know yet the value because we cannot get that yet, but we know the direction already. And we will draw also the acceleration of B normal, which you also computed a while ago, and that is 1.345 inch. So we know that the acceleration of B normal has a direction towards the axis of rotation of B, right? Same with A. So now B has the absolute acceleration of B has a normal component towards Q4. So that's why we draw it from Q also. So the direction is the same. So you can see here, they have the same direction. So it is also downward because the direction of the normal component is towards the center of rotation, which is Q4. That's why you can see here from Q, we draw the absolute normal component also from Q in that direction. So now that we have that, we can draw also the, we can now get the tangential component. So the tangential component of the acceleration of B is perpendicular to BQ4, right? Because it will be, Q4 is the center of rotation, so meaning its tangential component is perpendicular to BQ4. So we draw a line which is tangent to that. So as you can see here, these two lines are parallel. So meaning this line here is tangent to Q4B, and we draw it at the head of the normal. So same also the way that we draw the tangent a while ago to the normal. So we draw it from the acceleration of B normal, its head, and we do not know also its end because we do not know the value yet, the actual value. So we get the direction of the acceleration of B tangential. So the intersection of these two tangential points, the acceleration of B relative to A tangential and the acceleration of B tangential, represents the acceleration of B. So it represents the acceleration of B. How would we know that it is correct? Because if you're going to look at it, if we go back to our formula, the acceleration of B is the acceleration of A, which is this arrow here, plus the acceleration of B relative to A normal, plus the acceleration of B relative to A tangential. So you can see it follows also the original formula. So that's why the intersection represents the acceleration of B. Using also the other points, so we can see that the acceleration of B is the acceleration of B normal plus the acceleration of B tangential. So this line now here is the acceleration of B normal, and this line here is the acceleration of B tangential. So that's how would you check. So for the absolute acceleration, the origination of its, when you plot it, is from the Q, but for the relative, it is from the head of the other points. Just like for example here, B relative to A, so it is not absolute, it is relative, so that's why we draw it from the head of A. Same also here, the acceleration of B, tangential, it's also relative to this line here. So that's how we can get the unknown acceleration. So we're able to get acceleration of B. So now in our acceleration polygon, we already have the acceleration of A, and we also have the acceleration of B. So now we are going to locate the acceleration of C. So now that we have the 2 points A and B, we can also get the acceleration of C. We can actually get D, but we will first solve the acceleration of C since C is connected to A and B. So we can draw that by using our idea that the acceleration polygon is just a mirror image of the actual drawing. Take note that the point A, B, and C forms a triangle. So therefore, in the acceleration polygon, point A, B, and C should also have a triangular geometry. So how do we do that? So we can use actually our logic. We first join A and B, and AB is the acceleration image of the AB in the drawing. So the small AB, so this AB here in the acceleration polygon, is the acceleration image of the AB in the given linkage. So we draw that, so that that is the AB, that is the image of AB here. And then we lay off AB prime equals to AB. So meaning from point A, we draw we locate a B prime, which is equivalent to the length of AB. So this length AB here. So we draw that from A. So this is the AB prime. So you can see that this AB prime, its length is the same as AB. So you measure this one with a ruler, and from point A, you draw AB prime. So the direction is towards B because we wanted to get the mirror image of AB in our acceleration polygon. So that is the AB prime. Also, we draw BC prime parallel to BC. So because BC prime, B prime, C prime would represent also the acceleration image of BC. So you can see here, this is the B prime, C prime, and we have here the BC. So this now represents the acceleration image of the BC in our linkage, the B prime, C prime. So now we can look, we know already the distances of A to C prime and the B prime to C prime. Then we can also copy that in the acceleration polygon. So the best way to do that is to use A as the center and a radius equal to AC prime, we draw an arc. Also with B as the center and a radius equal to B prime C prime, we draw also another arc. So first we draw an arc with A as the center and the radius is AC prime. So this AC prime here, and point A is the center because we wanted to measure the distance AC in our acceleration polygon. So and then we'll locate C at the intersection of this arc. So how do we do that? So we draw. So you can see here, this circle here, this arc has a radius equal to AC prime. So we draw that arc. We draw that also in the acceleration polygon. They are the same circle. Same also with B. So with B prime as the center, we draw with a radius of B prime C prime. So this is the circle that we draw from point B. So take note that in our linkage, there are two intersections, and the intersection represents the C prime. Same also with our acceleration polygon. The intersection would be the C prime. So you can see we are able to locate the point C. So it also creates a triangle ABC. So we have here A, B, and C. So this is the acceleration image of this linkage here represented by A, B, and C. Take note that it should follow the sense also of the drawing. So that's why we select this intersection. We did not select the other intersection because it would not represent the actual drawing. This one represents the actual drawing. As you can see, we have A, B, C. We also have A, BC in our drawing. So this is the acceleration polygon. Then we can get the acceleration of C as the intersection, which is the absolute value is from Q to that intersection. So that is the acceleration of point C. So we're able to get the acceleration of point C. So now that we have the acceleration of B, acceleration of C, acceleration of A, then it's time to get the acceleration of D. So we locate D by laying off BD to line connecting AB. So we connect AB and then we lay off BD. So we can use acceleration and proportion because again, this acceleration polygon is just a mirror image of the actual. So by ratio and proportion, we get the value of BD as we can create ratios of this length here and also the mirror here. So we have BD over big BD is equals to AB over big AB, and then we solve for the unknown, which is BD, and then we substitute the values. So the AB has been measured as 2 point, so we measure this at 2.9. So this is the AB of the acceleration polygon, not the velocity polygon. So the AB of the acceleration polygon is 2.9, and the BD is the 6" here divided by AB, which is 15. So we can get BD by ratio and proportion, and that is 1.16. So therefore, the distance of B to D is 1.16 in our acceleration polygon. So we lay it off. So why is it that we place it there, not here? Because it should represent the drawing. As you can see, the connection is A, then B, then D. So that's why we connect it also as A, then B, and D. So if we connect it here, it will be different. It will be BAD, which is bad. It should be A, B, and D. So at that point, we can locate the acceleration of D. So as you can see, you are able to locate the acceleration of D. So now we are going to measure them with a ruler. So we see that the QA is 3.9 inch, QB is 1.63 inch, QC is 3.3 inch, QD is 1.52 inch in the acceleration polygon. So we calculate the acceleration of A, B, C, and D, which are the unknown, using an acceleration scale. We multiply these inches by 100 feet per second per second. So that's why the acceleration of A, the acceleration of B, the acceleration of D, and the acceleration of C will be obtained. So as you can see among the points, acceleration of A is the largest, and it is followed by the acceleration of C, and then we have the acceleration of B, and then we have the acceleration of D. So the purpose of acceleration, because if you know, for example, the mass of A, the mass of link A or point A, whatever that point A represents, then you can get the force, the dynamic force that is acting on that point by using the formula force is equals to mass times acceleration. And if you know the force, then you can know also the limitation, right? Because in our knowledge in mechanics, there are stresses or pressures that is being experienced because of the presence of that force. So we also have questions, which is to get the angular velocities of 3 and 4. So angular velocities as well as angular acceleration. So for the angular velocities of 3, which is this linkage here, ABC, which is 3, and angular velocities of 4, which is this one here, Q4B, we can use this formula. So the angular velocity of 3 can be obtained by using the velocity of B relative to A divided by AB. So we just measure the length of AB in the velocity polygon. So take note, because this is the velocity, not acceleration. So we measure AB from the velocity polygon, and that is 1.44. We multiply with the kV, and then we divide by AB. So that's why we have the angular velocities of 3 is 5.76 rps or rad per second. On the other hand, the angular velocities of 4 can be obtained by the velocity of B relative divided by Q4B. Again, we measure QB from the velocity polygon because it is the velocity. So we got 11.76 rad per second. Similarly, we will get the angular acceleration of 3 and 4 using the formula. Angular acceleration is the tangential divided by the radius of gyration. So that's why we have here the angular acceleration of 3. We measure the AB18 acceleration of B relative to A tangential from the acceleration polygon. This is the line here. That is 0.93 inch. Take note that this is the normal and this is the tangential of B. So that's why we measure that. And then we got 229 rad per second squared. So the angular acceleration of 3 is 229 rad per second squared. And also for the 4, the Q4B link, that is, we measure the tangential component of B divided by the radius of gyration. We got 93 rad per second squared. So see, we were able to obtain the different unknowns. So in this video presentation, you were able to understand how to use the relative acceleration polygon method in finding the acceleration or in doing acceleration analysis of points in the linkages. So if you are not satisfied with this video recording, you can also watch the video that presented here. You can click this link, you can watch them, and you can also learn from this video presentation how we can solve the acceleration. Thank you so much for listening.